So section 4.3.2, we are talking about the normal probability density function, okay? It's a really ugly function. If you're looking at it in the textbook, it's that huge thing, f of x, 1 over the square root of 2 pi sigma squared times e all to the power of that nonsense, okay? We don't really ever use that, okay? We're going to use Desmos here because Desmos is awesome, okay? We're going to start with number 472, okay? And this one is talking about the previous section that we did is talking about the race times, which we didn't do that problem, but I'll still give you the information that you need in order to solve this one, okay? Or actually not 72. We're gonna do 73, okay? Sorry. So if you wanted to use the relative frequency histogram to determine the percentage of women in the sample who have run times between 22.5 minutes and 24.5 minutes, you would have to add up the bars between 22.5 and 24.5. But our histograms don't do halves, right? We do wholes on those. We can use what we're going to learn today, which is the normal density function. Okay, normal probability density function, okay? And so I'm going to show you how to do that in the calculator, okay? So if you open up Desmos, go ahead and do that now, okay? You're going to type in normal dist and then put a parenthesis thing, okay? Right when you do that parenthesis, right below the normal dist with the parenthesis, it says mean is 0 and standard deviation is 1. Okay, so I'm actually going to give you your mean and your standard deviation for this problem because we need those in order to solve this. Okay, so for this, the mean time of the women racing was so x bar, right, because it's a sample. We went over x bar versus mu. X bar here is 23.2175. So 23.2175, okay? And then our sigma, or not sigma, our sample standard deviation, S, is 0.9729. Okay, so when we go back into Desmos, our mean is not 0, so we're going to type in our mean here of 23.2175, okay, 23.2175, comma, and then we're going to put our standard deviation in, so comma, 0.9729, okay, 0.9729, okay, and so now our graph is going to be totally wrong. So if we want to look at what this is doing on our graph, we need to scroll to the right, and we see that little bump there, right? That's our normal curve. We've talked about this, right? We've talked about the bell curve, okay? And so that's what this is now, okay? And so it wants to do a normal distribution curve from 19 to 27. So if we wanted to, on our x-axis, we could even go 18 to 28, okay, and then our y-axis really shouldn't be that much. Maybe start at negative 0.1 and go up to, I don't know, 0.6, okay, and if you do that, you'll see this nice curve, okay? So, again, we started at 18, and we went all the way to 28, and right in the middle, if we click on our curve there, it'll actually give us the top point, okay? So right in the middle here is our top point, and it's at 23.218, right? Because that's what our mean is. It's the same as our mean that we have right here. And then the probability at the top is 0.4101. So that's kind of the top of our bell curve. And then it goes down pretty steeply from there. Okay, so it's going to look something like this. Okay, So that's our normal probability density curve for this problem, okay? We type in our mean, we type in our standard deviation, and then it gets us our nice curve, okay? Now, the original question was asking for the area between 22.5 and 24.5 minutes, okay? And so our Desmos can do that as well. So we click on the find cumulative probability, CDF. So we click on the CDF box, and then it brings us this min and max, okay? And so the two values that they gave us 22.5 and 24.5. Those are actually our min and our max. And so if we plug in 22.5 as our min and 24.5 as our max, you'll see those get filled in on our graph that we've done on Desmos. Okay, so 22.5 and then 24.5. Okay, and you'll see this kind of like bar show up here and this bar kind of show up here, and then it fills in and shades in that area. Okay, and it tells us what percentage of women finished with times between 22.5 minutes and 24.5 minutes. So that's we got an answer here, and our area is 0.6759. Okay, so that's about 67.59%. Okay, 67.6% of the women finished with times between 22.5 minutes and 24.5 minutes. Okay, so that's how we use normal CDF. Okay, for part B, this was part A that we just solved right here. Okay, for part B, it says your model represents the percentages of women in the sample who have various run times. But it does much more than that. Since the sample of 40 randomly selected women represents the whole population of women who run in 5K races, your model can tell you about percentages of the whole population. If your model represents the whole population, what percentage of all women who run 5K races have race times between 20 and 25 minutes? Okay, so for part B, we're going to use the same mean and standard deviation, except we're going to just change our minimum and our maximum. Okay, so for part B, okay, our new minimum is going to be 20 minutes, and our new maximum is going to be 25 minutes. Okay, so let's go back to Desmos, and we'll just change those on here, 20 and 25, and we get 96.6% of the women have race times between 20 and 25 minutes. So that's almost everybody that races, right? Okay, 96.6%. That, again, that's almost all of the women that race in this, okay? Part C, that was part B, yeah? Part C, it says, although the fastest or smallest time in the sample of 40 women was 20.6 minutes, the normal probability density function that you're used to model the population starts at negative infinity and goes all the way to positive infinity. Okay, so what percentage of all women in the population run faster than 26 minutes according to our model? Okay, and so now we're going to go to Desmos, and our minimum, we want it to go to negative infinity, so we literally just type in negative infinity, and then it'll pop in the infinity sign for you. Okay, and then our maximum is going to be 26 minutes. So minimum, again, type in negative, the negative sign, and then infinity. Okay, and then our maximum is going to be 26. And so if we look at that percentage is 99.8% of the women run faster than 26 minutes. Okay, so almost the whole population at that point runs faster than 26 minutes that do these marathons. Okay, I'm not talking about all women in general, right? Normally, if you're going to do a marathon or whatever these are, this is not a marathon. I think it's a 5K. Yeah, it's 5K. So the women that run these, it's 99.8%. okay? We'll finish faster than 26 minutes, okay? So that's part C. Lastly, part D, we have what percentage of women in the sample run faster than the mean time? Okay, what percent of women in the population does the model predict will run faster than the mean time? Okay, so now, instead of our minimum is still going to be negative infinity. But now our maximum is going to be the mean. And the mean was this 23.2175. So max is going to be 23.2175. Okay, so let's change that on Desmos again. 23.2175. And if we look, that's exactly 50%. Why is it 50% again? Okay. It's 50% because that's the mean, right? That mean splits up the bottom 50% from the top 50% of this model. Okay, so we would expect to get 50%. If we went the other way, if we started with our mean, right, at 23.2175 and went to positive infinity, we would also get 50%, but it's the top half that would be 50%, okay? So, there you go, okay? Number 74 now, okay, is talking about the visors that we did last section as well, okay? So now they're saying that this company expects 775 racers. Okay, so we are in problem 474. Okay, 775 racers. Okay. And they need to find the hat size distribution for all women, okay, so that they know what the correct order for hats to order, right? Okay. So now we're going to make our model, okay, using the information that we have from that problem. Okay, so this is part B. Part A is just rewriting your histogram. You can just go back and look at your histogram. That's fine. I don't need to recreate that. But if we want to make a normal distribution problem, we need our mean and our standard deviation. So let's get those from that last problem. So our x bar, which is the mean, is 53.3325. And then our standard deviation was 1.1192. Okay, so that's our mean and our standard deviation. So let's plug those into our normal dist on Desmos, right? So that's weird. Sorry, I kept like all the other stuff. So our mean is 53.3325, and our standard deviation is 1.1192. Okay. Again, if we're typing that in, we do normal dist. Okay, and then we do our mean 53.3325, comma our standard deviation 1.1192. Okay, that's a 1 there, not a parenthesis. Okay, so that's what we type in, and then we're going to get another bell curve, right? Another normal distribution curve. Okay, so this one looks like it starts at about 49 and goes up to about 58. At our highest point, we are at 53.33. So 53.33, that's our mean. And our y value, the probability, so 53.33, our probability is 0.3565. So it's a little bit lower than where it is when we found our relative frequency yesterday, okay? Because it's more spread out, right? It's more like a bell curve than just singular bars. Oh, that was terrible. Okay, that side looks a little better, but whatever. Okay, so now we're going to use this to help us solve questions or answers, right, from these questions in parts C, D, E, and so on. Okay. So part C, it says, using your model to represent all women running 5K races, determine what percentage of women wear a size 51 hat. Okay. So remember, size 51 hat was from 51 to 52. Okay. So for part C, our minimum is going to be 51 and our maximum is going to be 52. Okay. Yep. All right. So if we type that into Desmos, our minimum is 51. Our maximum is 52. And we get about 9.8%. Okay, 9.8%. But the problem was asking, okay, no, it did ask percentage. So how did the percentage predicted by the model compare to the percentage observed in your sample? So what was our percentage yesterday? I was trying to remember. Is it 9? 9 over 40? Or no, 51 was the first bar, right? So 51, I think it was 5 on the histogram from yesterday. I guess I can pull it up. Let's do that really quick. Yeah, I think it was 5 from what I remember. Okay. Yep, 5. And so that would be 12.5%, right? So what we observed was 12.5%. When we did our normal distribution, we got about 10%. So it's a little bit off, but it's still pretty close, right? And when we're dealing with like real world numbers, it's going to be off, right? It's always going to be off because what we predict and what we actually see happen is never completely lined up, right? So it's close, but it's not perfect, okay? So then part D asks us, okay, how many size 51 hats should we order for the 775 racers, right? So if we had 775 racers, at, we'll say 10%. Let's just round it up, 10%. Okay, at 10%, then that would be about 77 size 51 hats. Right? And we'll round that down because we rounded up to 10%. Okay. Maybe we should just check just to make sure. What was 0.098 times 775? That's 75.95. So 77, 76 hats, somewhere around there, right? Probably 76 hats, because that's what this was, right? So let's just go with 76. Okay. So that's part D. We use our percentage to help us find kind of those real world numbers, right, from our normal distribution curve. Okay. How many hat sizes smaller than 51 are we going to have? Okay, so now for part F, okay, our minimum is going to be negative infinity now, and our maximum is going to be 51, right? Because now we're going to see how many hat sizes less than 51 are we going to have. So we have negative infinity and 51, okay? And so I get 1.9%. Okay, so 1.9%, and if we multiply that by 775, then we get about 15 hats. So 15 hats are going to be less than size 51. Okay, so there you go. Cool. And I think that's pretty much it. Actually, that was E, not F. there's one more for f, but it's basically the same thing, right? We're just plugging in values for our minimum. We're plugging in values for our maximum. So at this point, you're going to do your learning log. Okay, so this is number 4-75. Your learning log is on relative frequency histograms and normal distribution. Okay, so we talked about relative frequency histograms yesterday, right? Relative frequency histograms and normal distributions. So that's what we're adding today, right? And we can do that on our laptop, which is nice. Okay. So do your learning log. Remember normal dist, right, on Desmos. You type in your mean, which is X bar, and your sample, right? And then we find the minimum and the maximum. We can find between two things. We can start at negative infinity and find a maximum, or we can start at a minimum and go to positive infinity, right? Talk about all those different things. And then, that's it. So thanks for hanging in there. This was kind of a longer one, but this is actually important stuff. So thanks for listening, and bye-bye.